Morning, everybody. You sound sort of awake. You came in with a little bit of energy. At least you weren't like everybody on their social media, together but apart. That's great. Fantastic. What class is this? 4A? Okay, good, because I've been looking at 4B all morning, trying to get ready for that. What the heck am I doing? Oh, we were here, right? We had started this one and hadn't gotten really into it. But I gave you the kind of the big hint, the big reveal. What do we do with the straight line section? 1D. It's a 1D problem, right? It's the problem of something goes 75 meters, accelerates at 2.6 meters per second, right? What do we need to find out? In order to be able to answer the whole question, what do we need to know about what the car does at the end of the hill? No clue. All right, that's good. We'll start with nothing and we'll work towards something. Or maybe my question was really strange. Let me get the toolbox up here so at least we have something to refer to. While I'm here, let me just mention, there are other equations in the book, in this chapter, okay? One of the ones that tends to pop up a lot, I never remember what it looks like because it's totally useless. The range equation, well, it's not useless, but this doesn't help that much. It's called the range equation. Sometimes it's written as delta x, sometimes it's written as r, and it's like something something sine 2 theta over something something something. Okay? A lot of, if it's not one of these 3.5 or 4, then it's usually a special case. For example, the range equation only works if the projectile is launching and landing at the same height. And it can be difficult sometimes to realize that they're giving you an equation that has like really special conditions on it. Okay? So beware, right? Other equations, other formulas that you'll see as you study, okay? Those other equations come from these, right? This is like the master toolbox. These will always work. Other solutions could be very specific. We're going to do a specific solution today that we can use over and over again. But I'll let you know like where it works and the limitations of it. But here we go. Okay, so we need to find the final velocity of the car. It's starting, stop pointing at the screen, Mr. Bailey, just use your laser pointer. Okay, it starts up here, rolls down, gets to this end point. And if we're going to solve anything about the projectile motion, what do we need to know? Yeah, we need to know how fast it's going right at this point, right? Whatever this final velocity is for this first part becomes the initial velocity for the free fall section, right? So our plan of attack here, right? Okay, plan, right? Solve for V, the V final for the hill, right? Make that the initial velocity for the free fall, right? Just kind of laying out what I'm going to attempt here so that I can remember when I come back to it, right? So I'm solving for the final velocity on the hill. That becomes the V naught for the final, and then figure out, like, solve for whatever it is they're asking me for. Solve for parts A through C. Okay, so that's my overall general idea. Let's execute the first part here, the 2.6. Okay, so I know delta x. This is my how far it went. That's my acceleration, and I want to know final velocity. Which one? Can I do this one? What's missing? Time. This one? Right? Why is this one good? I want to find this. Do I know this? Yeah, it starts at right. Starts at rest. Starts rolling down the hill. Okay. This. Yeah. This. So Third equation, oops, can't even write it down right, equals v naught y squared plus 2a y, Mr. Balogh, oh my gosh. I'm sorry, you guys, my brain's just not here. Why am I writing down y's on things that don't need y's? There we go. 2a delta x. There we go. We're doing a one-dimensional problem here. I'm not into the free fall yet. Okay, so this is going to be the square root of 0 squared plus 2 times 2.6 times a positive 75. It's only moving in one direction. All right. Now, this is going to give me a positive and negative answer. I mean, it's moving down the hill. We can decide to call that direction positive, I suppose. Did I do that? Did I actually? I did. 19.8 meters per second. So, it's a positive or minus 19.8 meters per second. But now that I can do the second part here, we'll do that one in blue, okay? For this free fall section right here, okay? My initial speed is 19.8 meters per second. At what angle? This is not coming off horizontal, is it? It's coming off at this angle, right, of 15 degrees below the horizontal. So this is 19.8 at 15 degrees below the x-axis, or the horizontal line, right? So that is a vector, yeah?
So even though we treat that as one-dimensional, we can't say that this was Vx, it's just velocity.
Vx, Vy, Vs, Vr, I don't care what label we put on it. Well, it's one dimension, so basically it has two directions. Yeah. All right. It's a vector because it has both magnitude and direction. So maybe even before, like maybe we're just a little bit lost, not sure what to do next. If you're given a vector in this chapter, what do you do with it? Split it up into its components, right? So we're going to draw maybe just a little coordinate system, a vector. Doesn't have to be exact, just has to kind of anchor so that you can figure out what's going to happen next. Okay, it has an x component and it has a y component, right? X component, sine or cosine? Cosine. Why was it that fast? It's touching the angle. So V naught x is going to be 19.8 cosine 15 degrees. And is that a positive or negative thing? Is the x direction pointing in the positive or negative direction? Positive. And then V naught y is going to be 19.8 sine 15 degrees because it's not touching. And is that positive or negative? That one is negative. And why is the y component negative? It's pointing down, right? You'll notice there that I didn't put in negative 15 degrees. I learned very early in my career that if I start using negative angles, I'm just going to mess up, okay? So instead of putting in negative degrees and sort of trusting my calculator to, it flips negatives and positive signs depending on what you're doing. I'm just going to put in always positive angles and check my directions from a picture, okay? You can do it differently, but that's how I've noticed that I make the fewest mistakes. Draw a little sketch. I can just look at it. Oh, okay, I know x is positive. I know y is negative. I'm going to put a negative sign on the front of that velocity. How important are these signs? Very, very important, right? We've got to give the tools the right information. If we don't, we could end up doing imaginary physics, or even worse, we could get actual answers and it would still be like, right? Yeah, it would just be wrong. Okay, so we know V naught x, we know V naught y. What else is in our list of things we can know and not know? Let's see. So we got that. Oh, that's not in our list. Do we know the final y velocity when the car hits down? No. Okay, right before it hits, we don't know what that is. Okay. I know V naught y. AY, do we know AY? negative g, or negative 9.8 meters per second squared. Negative sign because why? It's pointing down. Not because gravity's negative, not because little g is negative, but because gravity points down.
When you found the final velocity for that equation,
Yeah.
wouldn't it be 171 meters per second? You're squaring the 75 and multiplying by 66.
Did I do my math wrong? 2 times 2.6 times 75 square rooted?
You don't square the 75?
No. To a delta y.
Oh,
Yeah. But you guys should always check my math. Like, I'm one of the worst people when it comes to numbers. It's just terrible. Yeah, we're good. My wife does not let me near the budget. Not because I'll just spend all the money spending. I used to be like that, and then I got married. It's because I can't like add or subtract. It's like it just. I don't know what happened. I started learning differential calculus, and the arithmetic left. It just left. Apparently, I had limited storage, and times tables got kicked out. My daughter, she was, golly, she must have been like in the second, third grade. Came home, Daddy, I can do times tables faster than you. I was like, okay, let's have a contest. She whipped me. Absolutely, Daddy, I can do it faster. And I was like, okay, here's a differential equation. Good luck. All right, yeah. I should bring my kids in someday so you guys know that they turned out to be okay. All right, so where was I? All right, AY we got. Do we know time? No. Do we know delta y?
We do.
Oh, we do?
We go down 150.
Ah, you said down, Liam, so that means what?
Negative.
Ah, the all-important negative signs. Check those signs. Leave a note to yourself to check the signs on every number you write down. Because you start with the wrong ones, you're going to end up with the wrong ones. All right, delta y, they're going through the lid, did all those already. Delta x, anything about delta x? No, we know that, but we don't know. Okay, so delta x is the last thing I don't know. All right, so what do they want? You notice how far I got? And I'm not even really concerned about what I'm trying to find. I need to get oriented. I need to get set up. I need to have a plan, just in general, about how I'm going to move through these things. And then I start asking I know it's easy to just jump and go, okay, what are they asking for? I'm going to solve for that. Or, part A, how far? What's the equation for how far? Right? Get the context. Context is so, so important. It'll save you time. It really will. How far from horizontally does the car land? What are they asking me to solve for? Right? They want the horizontal distance, right, from the cliff. But to find that, this is the only equation I've got. What do I need? I need time. Do they ask me for time? Oh, how long is the car in free fall? So am I going to do B first? Yeah, right? I got to find the time anyway. So I'll then use that time. What am I doing right now? Teaching Mr. Bailey. I am strategizing, right? Trying to model these problem-solving steps for you, okay? I strategize, I look at what I've got, I step back, I visualize, I re-strategize. I haven't done any math yet. Okay, I did in the red, right? But for this part, I haven't done any math. So I'm going to find the time, and then I'm going to find the range. Okay, how do I find the time? Okay, well, I could do that. And we know what happens when this happens. Quadratics, right? Okay. What is the magnitude? They're asking me for more stuff. What is the magnitude? Oh. They want to know how fast the car's going when it strikes the water. So eventually I'm going to have to find this component, aren't I? To be able to answer how fast it's going, I need the final y component, I need the final x component. So since I need to find basically everything anyway, and I'm feeling quadratic averse today, The other way to do this that we learned last time is that we can use the third one to solve for Vy. Like we know the initial, we know the acceleration, we know delta y. So we can find the vertical component when it hits the water, right? And then we can use that up here to find the time. Again, more algebra but less quadratic. And then with that time, I can come in here and go, okay, I can find the range. Wow. Right? Okay. Yeah. And you thought English was hard. All right. I don't have any room for this. I've really just sort of painted myself into a corner, haven't I? That's what new pages are for. Okay. So let's copy that. Okay. Do I have two of them now? No. No. Just want to add a page. Paste. There we go. Okay, so let's get rid of, on the copy, let's get rid of, we don't need this right now. Let's get rid of this and get rid of that. Okay, we're left with all of this. And then we'll just clean up a little bit. Sorry. Editing in real time here. We'll just move that kind of over there. And maybe that'll give us just a little bit of room for figuring this out. Let's go for solving the third equation. Vy squared equals v naught y squared plus 2ay delta y. Solving this means the square root. I'm doing math now. V naught y, which I know, don't I? Oh, I do. Negative 19.8 squared. That negative sign is inside that square, so it's going to disappear. Plus 2 times a negative 9.8 times a negative 150. That's going to give me plus or minus. Oh, thank you. I never finished this. This turned out to be negative 5.11, right? And then this one, according to my page, is 19.1. Thank you. So this, see, make mistakes all the time. That one was not intentional, like some of my mistakes are. All right, so there we go. Got the y, Good. Didn't put x in. It's usually something I do. I got 54.5. I'm not sure because I can't read my own writing. 54.5 meters. Okay, so that's a plus or minus answer. Which one are we going to pick? Ooh, 50-50 chance. I heard both answers. Which way is this thing going when it strikes the water? Down. So which one are we going to pick? Negative. So my Vy now, Vy is negative 54.5 meters per second. So is that the end? Can I just type that into the answer box for C? Vy is not the velocity it has when it strikes the water. Because what else is it doing? It's also moving horizontally, right? It's got a Vy of negative 54.5 and a Vx. What's the final Vx? It's 19, good, positive 19.1. Why is Vx the same as V naught x? We don't change stuff in the x direction in chapter 4. Projectile motion, there's no acceleration. The only acceleration is gravitation. So, now that I have these, how do I find the actual magnitude of the vector? If I have the two components, what do? For the angle, use the tangent, right? If I want the magnitude, I get old dude, Pythagorean theorem, right? Okay. So we'll just, since we're here, we'll do that. 19.1 square, squared, plus 54.5 squared. Where'd the minus sign go? Yeah, I got squared, 57.7. That's the magnitude of the velocity which is what they asked for. Magnitude means number, right? Just the strength. I don't care about the angle. So that's how fast it's going when it strikes the water. We did part C. Hooray for us. Okay. Part B. Let's use the first. So that was part. Mr. Bailey, you got to do a better job of labeling stuff. All right. Part B. V y equals v naught y plus ay times t. So solve this for t. That's going to be vy minus v naught. I'm doing math real fast here because it's painful. My negative 54.5 goes in there, minus a negative 5.11. A lot of minus signs for minus 9.8. For that time, I got 5.04 seconds. If I wanted to check that, what would I do? If I wanted to check to make sure my 5.04 seconds for the time is correct, what could I do? I would use the second one. I'd suck it up, do the I'd make Wolfram Alpha do the quadratic for me, right? But like, if I got the same time using the second equation, then I know we're good. We'll fly dangerous here. And so finally, how do we find delta x for part A? Right there, right? V naught x times t, which is going to be 19.1 times 5.04, which gives me 96.1 meters from horizontal distance from the wall. It's a lot of stuff, isn't it? How are you going to help your brain keep track of all the information that's being fed? I mean, practice helps solidify it, but like, take a step back from the practice, right? What methods are you going to take to help your brain keep track of information? You write it down, okay? You're strategizing, but write that strategy down. I'm a very poor example of this because I just verbalized it to you, okay? So that's because my writing is really messy and it just doesn't help my students. So I chose to verbalize, right, my plan, okay? I really suggest you write down, okay, your plan. Maybe try not to make it as messy and disorganized as my brain. This is perfectly organized, but for you, I'm sure it's just all over the place. But make sure that you are writing down information. If you ever find yourself just holding a piece of information in your head like a number, you're doing it wrong. Because it's gonna get confused with something else. Okay? So write down. Use 5 pages for one problem if that's necessary, right? Like, the trees are okay with it. I've talked to them. I'm a tree hugger, certified tree hugger, and they're okay as long as we're using trees for knowledge. Yes.
Why was we not at 19.8?
19.8 cosine 15?
Wasn't it 0?
No, it comes off the cliff at 15 degrees below the horizontal. So it doesn't come off the cliff perfectly horizontally. If it came off perfectly flat, then it would be 0 degrees.
No, like, wasn't it 0 meters per second? Like its initial velocity?
This is an excellent question. It was 0 up here. And as we do this entire section, this is not free fall. Everything on the screen I just right now is this section right here. We did this red part is this section right here. We had to break this up into 2 parts because the acceleration changed. These tools can only deal with an acceleration that stays constant.
So it's a one-dimensional problem, even if it's slanted like almost at 80 degrees, acceleration acceleration is whatever they give us, it's not the gravity one, right?
Correct. If it's gravity, then you know you're in free fall. You're not on a hill anymore. And by one dimension, I meant like the displacement, the acceleration, the velocity are all in a line. They don't have to be the same direction, but as long as they're all on an axis, it doesn't matter what that axis is doing, right? The problem with free fall projectile motion is that there's two things happening. We've got accelerations pointing this way, we got velocities pointing whichever way, and so that's why we have to break it up into x and y.
And then even if it's slanted, delta x is still whatever distance it
Yeah.
travels. Okay.
Yeah.
Because I thought we had to do delta y because it was traveling at a downward angle.
Yeah. No, that's what everybody wants to break it up and make it harder than it is, and it's not. Then if they had given me acceleration components down the hill, then I would have just cried and changed the major. But like, yeah, no, if it's all lined up, one-dimensional problem. Good questions. Love it. All right, what are we doing now? Doing a quiz! There we go. Okay. Okay. The part that today you're going to hate, but is going to save your bacon over and over again. Because what I'm about to do is do an example. So up to this point, we've known what the initial velocity is. We can find the component, like we give you a speed, we give you an angle, you break it up into its components. We're going to reverse that, right? We're going to set up a situation where we don't know what the initial velocity is. And we have to go find it. Lots of different situations this could have, but I want to go full bore physics on you. And what I mean by that is physicists like to do a problem once. If we solve it once, then we never have to solve it again, right? That's the goal. Okay? In physics, we call it grand unified theory. We're trying to get an equation that represents like everything. Not an equation, but a system. Anyway, what do I mean by this? I'm going to do this problem as generally as possible. In other words, I'm not going to put in any numbers. This is going to be all symbols. Okay? And I'm going to try to set it up with the least number of restrictions on it, which can be kind of hard. But let me just start and let's see what happens here. So we're gonna launch something at an angle theta with an unknown initial speed. Well, we gotta have something, okay? And that's the information that we are going to have, okay, is that we are going to know what the delta x actually is. We're going to know the horizontal range. I better make a list over here, okay? What do we know? We know delta x, okay? That's an x, okay? We're also going to know our delta y. These delta y's and these delta x are going to correspond, right? So when it's a horizontal distance over, it's a vertical displacement. It could be up or down. I drew it up, but it doesn't have to be. So I'm going to know my delta y. We're also going to know the angle that we throw this at, because if we don't, then it becomes a real bad day. Okay, and I think, yeah, that's it. We know the angle, we know the delta x, and we know the delta y. And maybe I'll include it in the list, but I don't really consider it like yes, it's a known value, but we know that the acceleration is in the y direction and negative 9.8, right? Like that's good, okay? Because it's a projectile motion situation. So what are the limitations of this setup? Kind of good to know, right? Going in. So what do we need to know? Angle, delta x, and delta y. If we know those things and it's in projectile motion, then what we are about to do, the equation that we are going to get to, will apply for every situation where we know those three things. Any situation, right? We know those three things, we can find this velocity. Okay, so what are we going to do? What don't we know? Like, From the toolbox. Do we know final velocity? Y direction? No. And we don't know V naught Y. We know that. Do we know the time? Okay. We know that. Okay, good. No. Yes. No. There's a lot of no's. No. No. Yes, yes. Yes. No, no. That seems like a lot of no's, like things I don't know, right? And so, how do you approach something like this? Well, a lot of times you just start throwing partially cooked noodles at the wall to see what sticks. You guys know that trick? Supposed to throw your spaghetti at the wall. If it sticks at the wall, it's done. That is not how you tell that spaghetti is. My grandmother caught you doing that, it'd be a wooden spoon across your head. Okay? How do you tell if a noodle is done? You eat it. Right? And if it's got the right texture, it's done. If it's mush, you went too far. If it crunches, probably needs a little bit more time. All right, so cooking with Mr. Balogh, that's where that went. What's something that kind of ties it all together that seems to crop up a lot? Yeah, but we don't know that. We're going to try to find it. We know we want these things, right? We want these V naughts. It's in all but one of the equations consistently. It's hunting. You can't avoid it. Time. Time's everywhere, isn't it? Except in this third equation, right? So is there a way for us to get rid of it? Is there a way for us forward that allows us to maybe solve for a time in terms of one thing and then like substitute it into, like, substitution's a great way to get rid of something we don't know, right? So I'm looking at this fourth equation right here. I know delta x, right? I want this V naught. I don't know this. I know I've got to use this equation. How do I know I have to use this equation? I know delta x, right? It's a piece of information I do know. And so I got it. So part of my strategy here is going to be, okay, I know I'm going to be using this one. It's going to be a part of what I'm going to do here, right? So what's another equation that has other known things, something other and something else I'm looking for, but also time? Yeah, the second one in the y direction, right? Because I know delta y. I'm looking for a v naught. I know my acceleration, but again, my time is unknown. So what is this set up? V naught yt plus 1/2 ay t squared. Okay, so okay. How many unknowns are there in these two equations? That's an unknown. That's an unknown. There's 2 in that one. This is a third unknown. There's 1, 2, 3 unknowns. The t is the same, isn't it? That's just a repeat of 2, isn't it? So I've got 3 unknown things and only 2 equations. In mathematical circles, that's called impossible. If you have 3 things that you are unknowns that you are looking for, and you only have 2 equations, system of equations, you cannot solve for all 3 of them. Heck, it's really hard to solve for even one of them. So what do we need? We need a third equation, don't we? Okay. And in this case, we actually need 2 more. And v naught y as what?
V naught sine theta. V naught cosine theta.
Yeah. Remember, there are components here. We need those components, don't we? This is a projectile motion problem. And so we need to break up our velocity into its component parts. And so now, if I substitute those in, delta x, it looks worse, doesn't it? Delta y v naught sine theta t plus 1/2 ayt squared. Okay, that got worse because it looks worse, but it got better. Why did it get better? How many unknowns are there now? 1, 2, 1, 2. We managed to get rid of v naught x and v naught y, but we knew kind of what their relationship is in terms of the components of the vectors. So now I'm down to 2 equations with 2 unknowns. Independent of my skill to do algebra, is it possible mathematically to get an answer? 2 equations, 2 unknowns? Yeah, this can be done. Let's see if Mr. Balogh can do it again. I've done it lots, but that's no guarantee that it's going to happen. Notice the strategy is forming as I look at my tools and I look at what I've got to deal with. Overall, if you're ever given a problem where you need to find the initial velocity and you kind of don't know where to start, your general strategy needs to be, well, I got to use this one and the second one. I got to use the delta x equation and the second one. If I can get there, right, if I can start there, chances are I'm going to be able to work this out. All right, so let's see here. Algebra is now going to ensue. I will try to show as many steps as I am capable of. What's the same in both of these equations? V naught and time. What do I want? V naught. So I'm going to solve for time. It's always weird to me, right? If I'm looking for V naught, the first thing I'm going to solve for is time, but that's true because what do I need to do at that time? Substitute it out, right? I want to kind of get rid of it, right, by substitution. So let's see here. We'll do it in purple. This delta x, if we divide both sides by v naught cosine theta and make it look really sloppy, we'll get time. Okay, so I just, the v naught cosine theta, I divide both sides by it, and I get that. Okay, now that time is going to get inserted there and there. So this delta y equation, hold your breath, v naught sine, no, don't hold your breath, breathe, nice and even, it's going to be okay. V naught sine theta times, and now I substitute in the t, that's going to be delta v naught cosine theta, oh boy, plus 1/2 ay, all this junk squared, oh my gosh. Okay. Ah! I know. That's awful. But is there a ray of sunshine? We only have one unknown, which is good. It's showing up in a lot of places, though. But what's going on in that first term? What's a v naught divided by a v naught? It's 1, not 0. It's 1. 2 over 2, 1. 4 over 4, 1. V naught over v naught, 1. Okay. What's sine divided by cosine? Tangent. I mean, I usually don't smile when tangent's involved, but any time that I can sort of compress and not get a fraction, I'm a happy camper, right? So my sine over my cosine becomes a tangent. The delta x is just there along for the ride, and the v naught's can. Woo! That's pretty good, right? Plus, and I don't have anything to help you over here. Ay times delta x squared all over 2 v naught cosine squared. Oh, there's another square. Okay, so I carried my squared through all the terms. The 1/2 was in the denominator already. Sort of cleaning stuff up there. Okay. What am I after? V naught sitting right there. So let's Let's take the delta x tangent theta and move it over to the side. What happens when you move it to the other side? It becomes a minus, right? So that's going to be delta y minus delta x tangent theta. That's going to be equal to all the things I left behind, 2 v naught squared cosine squared theta. Okay. Whoa, what happened? I wrote that in like a...
How many times by day you divide
Okay, yeah, so let's see. Lots of the ways to think about this, but if I swap these two sides, in other words, I multiply both sides by 2 v naught cosine theta and I divide both sides by everything on this side, they effectively swap in their positions. So that's 2 v naught squared cosine squared theta equals ay delta x squared all over delta y minus delta x tangent of theta. And now what do I divide by? The 2 and the cosine squared theta. So that leaves me with v naught squared is equal to ay delta x squared all over 2 cosine squared theta times the quantity delta y minus delta a. Oh my gosh. This is just horrible. I'll write it down clear at the end. Now, what's the last thing I do? I've got a squared right there, so I've got to square root this whole thing, right? So this becomes, and I'll try to write it clearly now, v naught is equal to, and technically plus or minus, but we're not going to write down plus or minus, square root of ay delta x squared all over 2 cosine squared theta times the quantity of delta y minus delta x tangent of theta. Okay, what is sitting in the green box? The answer. The answer to every problem where you know delta x, delta y, and the angle. And it's a projectile motion problem. If you know those things, do you need to reinvent the wheel? No, we invented all the wheels. Okay? And you just need to insert the values delta x, delta y, and the angle. Make sure your calculator's in degrees mode. And you are done. This is an example of the power that physicists wield when we are trying to understand the universe. Yes, we have these toolboxes, and yes, you would always start there if you don't know it. But we can put them together in situations. I warned you about the range equation. The range equation is a powerful equation if you understand its limitations, right? This is a powerful result if you understand its limitations. I believe I gave you at least 2 problems on the homework that are asking you that maybe more to find the initial velocity. Okay? Give this a go, right? At worst, you waste, 5 minutes? Okay? Trying to calculate this, right? See if it works. Worked, great. Know its limitations. Know where to apply it. Make it a part of your toolbox, right? Some sort of Frankenstein screwdriver, hammer, spork thingy, right? And it'll have its use. It'll have its use. It's not a unitasker. It very definitely can do multiple things. How are your brains? Yeah, totally, right? Just shut down like, Mr. Balogh, you did one problem way too fast, and then you did this. I thought you liked it. I do like it. But I want to take about 2 minutes to inform you about something. I don't know if you've been aware of it, but I have been, I'm going to use this word carefully because it has a very negative connotation. I've been manipulating you the entire time you've been in this class? Has anybody noticed the manipulation?
Are you really like 4 inches taller?
What?
Are you like 4 inches taller?
Yeah, I'm really 4 inches taller, and I've just been, no. Yeah, okay, good. Yeah, Liam, you think you know what it is?
Maybe like something about wearing 2D.
No. It's not about the physics. It's about how your brains are working. Have you noticed that about once every 10 to 15 minutes or so, there's a very abrupt tangent? I'll seemingly get distracted, or I'll mention something, or we'll do a quiz, or something like that. That is very deliberate. There are 4 people in my family. 3 of them are attention deficit, and I am not one of them. I know how to keep my attention focused on stuff, okay? Why am I distracting your brain once every 10 to 15 minutes?
Yeah, studies say so.
What? Because studies say so? Yeah, we know all about psychologists. I don't trust them. No, I trust my therapist. To give it a break. What is the average adult's attention span?
10 seconds.
No. It's measured in minutes. It's about 10 to 15 minutes, depending on the individual, in natural light. Under fluorescent lighting, this is LED lighting, but it's got the same color spectrum. Under fluorescent lighting, that attention span lowers to about less than 11 minutes. The lighting has an effect on it. How do I know all this stuff? I made it my business to know. What's my business? What's my job? Teaching. It's to help you be the best you can be at this subject, right? And so if one of those ways is I can reset your brain every 10 to 15 minutes by giving it a distraction, I will do that. I'll do it with a hat. I'll do it with a stupid joke. I'll do it by mentioning some tangent that's going on in the news. Something, right? Because when I say, oh, wait, what are we doing? What just happens to your brain? It reorients and gets back, right? I couldn't do that if we had just been running the marathon consistently, right? We took a pause, we took a break, we got a drink, now we're back into it, right? So there's a lot of these things that I do, and I just wanted to come clean because I was feeling guilty for manipulating. No, I'm manipulating you, but I'm trying to get the best performance I can out of your attention spans, out of your brains, all that kind of stuff. So there is very rarely a waste of time in here. Almost everything I do is calculated to get you to perform the best. And I've heard some of you say it. I've heard some of you come up, Mr. Balogh, that class went fast. Or I can't believe that class is, we're done already? Then I know I'm doing my job. Right? The rest of you are like, oh my God, Mr. Bale is the longest class in the universe. Why do you keep talking like this? Right? But I just wanted you to know, I consider myself an expert in brain hacking because I've been doing this for 24 years, and I can see how, and yes, has the attention span been shortening? Yeah, I've seen the attention span shorten over the last 2 decades, okay? And I definitely blame social media for that one. So, all right. But I don't have any of the studies to prove it. That is anecdotal evidence. All right, let's do we have time to do the monkey hunter? Well, no, the problem is I got to finish chapter 4. Let's do, if you didn't talk about hacking our brains, Mr. Bailey, you could have done it. It's true. It's not that important. We'll circle back to it. Let's cover the last little bit of chapter 4, which honestly seems like it comes straight out of nowhere. It's like, what? Okay? The reason your author attaches it to the end of chapter 4 is because the particular situation we're going to talk about is another situation involving constant acceleration. And the author could have waited to do this all in the chapter when it comes to doing rotational motion, but I actually agree with this approach in that if we start exposing you to circular motion now, it won't be such a terror when we finally get to it. Okay? So even though this looks like it's coming out of left field and doesn't have anything to do with projectile motion, it has something to do with it in that the equations we've been using so far in this class all assume an acceleration is constant, not changing. Right? And so as another example of an acceleration that doesn't change, I have my tennis ball on a string. Okay? And this tennis ball is going around in what we call a vertical circle, okay? Because the plane of the circle is oriented vertically, okay? But if I keep the speed of this tennis ball the same as it's going around this circle, then it has a constant acceleration. Now, chapter 5 is where we're really going to get into forces and their directions and all that sort of thing. So just the very short version of this is, if I'm swinging this around in a circle and I cut the string, which way is the ball going to go? Tangent. It's going to move in a straight line. Tangent to whatever it was doing. Because if it's at this horizontal position, right, and I cut the string, it's just going to keep going in that straight line. Okay? Objects want to keep going in this first line. Okay? So the question now becomes, is this object accelerating? What's an acceleration? A change in velocity. And what's velocity? It's speed and direction. Right? It's a vector thing. Is this ball's speed changing? No. Is its direction changing? Yes. In a circle. It's constantly changing its direction, right? Consistently changing its direction. And so we can keep the speed the same and yet still have something that is accelerating. The acceleration, the name that we give to an acceleration for an object moving in a circle is called centripetal acceleration. It's a fancy old-fashioned word that means pointing towards the center. There he is, okay? It means pointing towards the center. And for any object that is moving in a circle, it will be pointed towards the center, and we can find it if we know how fast it's going and we know the radius of the circle that it's in. For our treatment right now, this is going to be a fairly easy, just find the acceleration, right? Or if you know the acceleration, find the speed, right? If you know the acceleration velocity, find the radius of the turn. But a couple other things you need to know about circular motion to help you out here. We have a term that we talk about the time it takes to go around the circle once. So this term applies to the International Space Station. It applies to my string on the ball, applies to the moon. Anything that's going in a circle around anything else, okay, has what we call an orbital period. Okay, we kind of came up against this with the period of the pendulum, right? Is the green really bad? Should I avoid green on this screen? Yeah, that's what I thought. You guys need to tell me these things because it looks fine on my screen. Is this green better? Does it not look green?
It looks black.
Looks black. This is black.
Yeah, you're pretty close. I mean, that other dark.
Yeah. Okay. We'll work on this. We'll work on this moving forward. We won't do it right now. I'll just switch to black for right now. But you guys need to tell me when something doesn't. Don't ever use yellow on a white background. It's like the first rule of teaching. Okay. That was a legitimate tangent. I hadn't planned that one. All right. So where were we? Okay. So the period, the time it takes for this thing to go around once, so capital T for a complete go around, is equal to the distance the object travels divided by the speed it was traveling at. Distance equals velocity times time. Rearrange it, and you've got that right there. Okay, so we can find the acceleration that something has going in a circle. We can know things about how long it takes. We like if I know that it takes half a second for my tennis ball to go around, and I know how big my circle is, right? I can find out what its speed is. And once I know its speed, I can find its acceleration. So again, I know it feels like it kind of comes out of left field, but they're trying to tie together this idea of equations for constant accelerations. Let's do a quiz, and then I'll do an. Okay. If you're standing on the equator of planet Earth, are you moving in a circle? Yes, because the Earth orbits on its axis. And in physics, unless you're told, in these classes, Physics 4 ABC, unless you're told otherwise, the Earth is a sphere. Perfect sphere. It's not. It's fatter in the middle. Smaller on the edge, like me. And bigger in the middle. Does anybody know what the actual shape of the Earth is? What that's called? It's an oblate spheroid. That's me flexing nerd on you. Don't worry about that. Okay? So, if we're going to find out how fast a person's moving, they're standing on the equator. Visualization. Here's the Earth as seen from the North Pole. We're looking down on the Earth, right? And a person is standing on the equator. So polar bear on top, person on the equator. Can't see the penguins. Okay. And let's say we're going that way around the Earth, right? Okay. How fast they're going? Well, I mean, what is speed? It's the distance over a time, right? And I gave you an equation that related distances, velocities, and times to each other, especially for things that go in circles. So that speed is going to be equal to the distance traveled divided by the time it took. Do we know anything about how far somebody goes if they're standing on the equator? What do we need to know? Okay, time. How long does it take for somebody to go around once? 24 hours. So the time is 24 hours, but can I put 24 hours into my equation? Not standard units. So then 1 hour, there's 3,600 or 3,600 seconds. Okay, so that's 86,400 seconds per day. All right, so I have my time. What else do I need? The radius. And what's the radius of a person's circle if they're standing on the equator? Half the diameter of the Earth, or in other words, the radius of the Earth, right? So what's the end? That's the North Pole. Just trying to indicate that we're looking at it top down. So what's the radius of the Earth? Well, how do you find out? Google, right? You get a lot of different answers because it depends. Most physics textbooks will agree that the radius of the Earth, I wrote it down here, is 6.37 times 10 to the 6 meters. 6,370 kilometers, or roughly, what is that, like 4,000 something miles? Pretty big. Okay? So we have the radius here. So that's 2 pi 6.37 times 10 to the 6 all over 86,400. Because I put meters in, I put seconds in, it's going to come out in meters per second. And so this person is moving at 463 meters per second. Which way? Right now, which way are we rotating? Towards the east or towards the west? We are rotating east. We are rotating that way. We're not going that fast, but we're rotating this way. How do we know we're rotating that way? Because sun go other way. All right. So there's how fast somebody at the equator is going. And how do I find the acceleration? Centripetal at that point? V squared over R, when I plug in all those numerals, 0.0337 meters per second squared. Directed which way? Inwards. Centripetal acceleration, that centripetal word tells you the direction it's pointing towards the center. It's an additional, we tack it on the little g sometimes. It's very small, right? Now, how fast is somebody going at the North Pole? What's their rotational speed at the North Pole? 0. I mean, okay, technically they do that in one day, right? Okay, but they haven't gone any distance, right? Okay. So there's a big variation between like North Pole and the equator. That measurement is called latitude, right? Kind of where you are with respect to the equator. And as you go higher up in latitude, okay, and here in the 42nd, 43rd degree of latitude, that might not exactly be right. It's in the 40s somewhere. It doesn't go linearly. It goes as the cosine of the angle between us and the equator. Okay, so I had this question once. So I have a learning disability. It's related to dyslexia, and they gave me questions once, and this was one of the questions on the exam. Right? The psychological, like, what do you know versus what can you get out of your brain? And they were asking me verbally, why do people on the equator move faster than people on the North Pole or something like that? And I just stopped in the middle of tons and tons of questions. And I said, do you really want to know the answer to that question? And the poor grad student that was giving me the exam was like, sure. I said, do you really want to know the answer to that question? She just kind of leaned back and went, okay. And so she stopped me about 5 minutes in. I was halfway through the derivation of the angular dependence of the speed, the rotational speed of the thing. She's like, what major are you? It's like physics. She's like, oh.
That's describe everything.
What's that?
That describe everything.
Yeah, pretty much. Kind of explains a lot. You know the fastest way to end a conversation
Stop.
is for me to tell people that I'm a physicist. Yeah. Like, oh, you're a teacher. That's fantastic. Oh, I love teachers. What do you teach? Physics? Oh. I'm used to it. I will see you tomorrow. Tomorrow's lab. Goggles. You need goggles in tomorrow's lab. If you have a favorite pair, bring them. If not, I will have goggles for you. Glasses do not work. You'll have to wear something over your glasses. Okay? So, just fair warning. We got you covered, but if you got a pair you like, bring them.